molecular interactions. So what we are interested here is to study the hydrocarbon contamination in confined areas. As most of you all are aware, surfaces, especially those of two-dimensional materials, have high surface energy, and hence they tend to attract many unwanted adsorbents, especially the hydrocarbons, which contaminate its surface and also alter its properties. For a very long time, graphene was known to be a hydrophobic substance because it had a very quick adsorption of hydrocarbons. But in real, graphene is actually a hydrophilic substance. Hence, we see that the surface contamination is very well studied. But what was lacking here was the study of contamination in a confined area. So in this study, we tried to understand the contamination in a confined area by fabricating angstrom-slit channels of various height and deliberately introducing surface contaminants. And this study is majorly important to understand the stability and performance of the devices in a very long run. So the device fabrication, we basically use a silicon wafer and create a freestanding silicon nitride membrane. On that, we use photolithography techniques to create a hole. And then we transfer a bottom two-dimensional crystal. Using the hole as a mask, we etch the two-dimensional bottom crystal layer. And then we use other e-beam lithography and reactive ion etching methods to fabricate a two-dimensional spacer of different heights, which would serve to understand the confinement studies. And then we deposit this two-dimensional crystal on the bottom layer, and we seal this whole device using a top two-dimensional crystal. Here, the most crucial part of the device is the two-dimensional spacer that is used to determine the confinement effect of the hydrocarbon contamination. So here we use an experimental setup which looks something like this. We mount our device on a sample holder and place it here that connects to two particular chambers. We introduce helium gas from the top side of the chamber, which travels through the channels and goes to the helium leak detector, which quantifies the gas flow. Here, the gas flow rate is measured per pressure to understand the channel's contamination level. We use a standard Knudsen equation stated here to calculate the gas flow and to understand the channel's cleanliness. So we started by studying the natural airborne contamination in these two-dimensional channels. For just a reference, this is the cross-sectional TEM image of how our device looks like. So if we, here we considered a 5-layer device, and hence the confinement area is about 1.7 nanometers. We see that when this particular device was left in air, ambient air, for about 10 days, there was a high decrease in the gas flow rate. That indicated that there is a partial contamination in these channels, and hence this clogging reduced the gas flow. On further keeping this device for 20 days, we see that there is a further decrease. But on annealing this particular device in a furnace using 400 degrees Celsius for 5 hours in the presence of argon and hydrogen, we see that the gas flow rate is revived to a greater extent. We also then put these devices in a charcoal, which acts as a contamination sink and a hydrocarbon adsorbent. We see that the gas flow rate decreases about 30%. This thing majorly shows us that the contamination in these channels majorly came from the hydrocarbon contaminations that were present in the air. Further, we then proceeded to understand the difference in these confinement behavior of the hydrocarbon contamination in a thicker and a thinner channel. So to compare that, we took a 3-layer device and a 32-layer device to see the difference in the hydrocarbon contamination. As clearly seen from these two graphs, you see that there is a 50% reduction in the gas flow rate in a 3-layer device, which is a thinner channel device, whereas there is a more than 97% reduction in a 32-layer device. We majorly attribute this reason to the fact that there is a difference in the interaction of the hydrocarbon molecule and the surface of different confinement. We also report here the previously reported paper, which says that in thinner channels, there is an inherent effect of self-cleansing action, which removes the polymeric residues. But in a thicker channel, these residues tend to stay, which may serve as a seeding for further hydrocarbon contamination. So in our studies, we then tried to mimic the hydrocarbon contamination using a model molecule. So as known, atmospheric hydrocarbons include many alkanes and volatile organic compounds. We use hexane for the following reasons. Hexane can be easily vaporized and hence was a better solvent for our experiments. Hexane also has a relatively stronger absorption on the two-dimensional materials, and the kinetic diameter of the hexane was chosen such that the angstrom slit channels, we could fabricate angstrom slit channels which were lower, higher, and of similar size to that of the hexane molecule. So we wanted to study about the influence of hexane in our slits. To understand that, we just modified our experimental setup. So as shown before, this is the experimental setup, but here we introduced this particular hexane bulb. So what we did here was we introduced our device and injected hexane, and we exposed our device to the vaporized hexane for some time. This could have a different effect based on the confinement available. It could have either partially or completely clogged the system or have had no effect. And then we measure the helium flow rate to understand the effect. Then we had two different ways of revival in these devices. So first was the helium flush method. In this, we just exposed our contaminated device to helium flow and tried to mechanically push the adsorbed molecules with helium gas. The other way we used was desorption using heat. So we just heated our device on a hot plate for about 150 degrees, and we were observing that there will be desorption of the hexane molecules. So basically, what we studied was the difference in the behavior of the adsorbed hexane molecule based on the height of confinement. So here we studied a 5-layer device where the height of the confinement was much larger than the kinetic diameter of a hexane molecule. Here we observed that the initial flow rate was very high, but on introduction of hexane, the channels clogged. But on the revival mechanism 1 that we followed using helium flush, we could revive our device to a greater extent. But this revival mechanism had its own limited efficiency, and hence we had to use another method, that was the heat method. And when we used that, we saw that was a complete revival of our device. Then we studied a 2-layer device where the size of the kinetic diameter of the hexane molecule was similar to the height of confinement. Here we see that there is a complete blockage of the gas flow. This could be due to the tight confinement between the hexane molecule and the two-dimensional surfaces. And we also saw here that we could not revive the device either by flushing with helium gas for very long hours or with heat. We later studied a monolayer device. Here we saw that there was no effect on the gas flow rate with the exposure of the hexane molecules. This was attributed majorly to the self-cleansing effect, which was reported earlier. And the slight decrease, we say that this is due to just the blockage of the entry blockage effect. So majorly in our study, we tried to understand the influence of hydrocarbons in a confined channel and discuss its clogging and unclogging by intentional exposure to hydrocarbon contaminants. Here we used a hexane molecule. Then we try to demonstrate that the confining dimensions of these angstrom scale channels have a greater effect on the severity of the hydrocarbon contaminations observed. We also demonstrate the stability of our nanochannels, which is up to 3 years, which is very high. And we provide a new and an easy way using a helium leak detector method to assess the cleanliness of the non-porous membranes. You can find this article in this journal. And yeah, I would like to acknowledge my group members and the funding agency, and thank you for your attention. I'm ready to take questions.
Any queries? Participants, any queries you can ask. Ma'am?
Yeah.
Why you specifically focus the hexane in addition of influence of hydrocarbon?
Yeah, so as mentioned here, hexane has, so we did try and think of many other available alkanes, but majorly the reason was hexane, we could easily vaporize it. So it was easier for us to do comparison. And also the channels which we fabricate are basically with graphene spacers. So depending on the spacer channel, it was easy for us to fabricate devices which were higher and lower confinement area for the hexane, for the diameter of hexane.
Thank you, ma'am. Any more queries?
Ma'am, can we use other hydrocarbons instead of hexane?
Yeah, of course you could, but again, you will have to fabricate such devices to understand how the effect would be, and there would be many other factors involved. We wanted a longer hydrocarbon because the absorption is higher. So yeah, of course you could try some other, but everything will have their own limitations. And for us, we came to a conclusion that hexane is the best.
Thank you, ma'am.
Any more queries? Okay, thank you, ma'am. Now I call Mrs. Tangam, Assistant Professor of Department of Physics, to give the chief guest introduction for the session 2.
Good afternoon to one and all present here. I feel privileged to introduce our chief guest, Ms. Archana. She did her UG in Bishop Heber College, Trichy, Tamil Nadu, and completed her PG specialization in organic chemistry at Christ Deemed to be University, Bangalore, Karnataka. She was working as a project assistant during the year of 2018-2019 at Central Electrochemical Research Institute, Karaikudi, Tamil Nadu. At present, she is doing PhD in physical and theoretical chemistry in chemistry department of University of Oxford under the supervision of Professor Richard G. Compton. She has published 9 publications in the field of chemistry, and she has received a lot of awards. She received Best Overall Oral Presentation Award in International Symposium on Advances in Electrochemical Science and Technology in the year 2019. She is a recipient of Commonwealth Scholarship for Doctoral Studies, UK in 2019, and recipient of Summer Research Fellowship offered by Indian Academy of Sciences at 2015. Now I would like to hand over the session to Ms. Archana. Ma'am, please.
I thank you so much for the kind introduction. I would like to share the screen. So good morning, everyone, and good afternoon to people in India. Today, my topic will be on the electrochemistry of single nanoparticle. So the objectives of today's talk will include electrochemistry, its brief introduction and applications, electrocatalysts and their introduction. I will be discussing my experiments and research. Further, I will move on to nano impact experiments, which is a single entity experiment. And then I'll conclude my talk along with acknowledgement. First of all, electrochemistry, as the name suggests, is the interrelation between electrical and chemical effects. So electricity, as we all know, is flow of electrons. So any chemical reactions that involves electron transfer can be studied using the electrochemistry tool. And that when there is a gain of electron in a chemical reaction, it's called reduction, and where there is a loss of electron, it's called oxidation. A typical example is given here, where the ferricyanide is converted to ferrocyanide. This is a redox reaction, which is coupled with a reduction and oxidation reaction simultaneously. We study electrochemistry in order to understand the thermodynamic and kinetic parameters like electrode potential, kinetic rate constant. So we need a tool, a technique to measure these things. And cyclic voltammetry is one such powerful and very efficient tool to study the chemical reactions. Here is a 3-electrode setup for the cyclic voltammetry experiments, which is contained of the electrolyte, which we are about to study. And we have the working electrode, counter electrode, and the reference electrode. Working electrode is where a reaction usually occurs. And the potential on the working electrode is measured with reference to the reference electrode. Counter electrode is helpful to complete the circuit, and also it checks the charge flow and everything else. So this is how a typical cyclic voltammetric cell would look like. So once we attach this setup to a potentiostat, we have a voltammogram. This is the graph which corresponds to a redox reaction. And this is how the cyclic voltammogram would look like. So when we apply different potentials, the current transient is thus recorded. And we have a reductive peak corresponding to the reduction reaction. We have an oxidative peak corresponding to the oxidation reaction. So what are the applications of electrochemistry? Why is there a necessity to study electrochemistry? Electrochemistry is applied in a huge area, which includes biosensors, your glucometer and your alcohol meter and chili sensors. Everything comes under the biosensors. We have a 3-electrode system, thus this is a glucometer. So we have a 3-electrode system here, and the glucose level in the blood is thus recorded. And the next application is energy conversion, where we have to like convert the electrical energy, like the chemical energy, into electrical energy. So that's where energy conversion takes place. And when we convert the energy, we have to store. That's where energy storage devices is useful. And my study is hugely focused on energy storage devices. Energy storage devices include your AA, AAA batteries to huge batteries that is used to light up the whole city. And then we have corrosion studies, where electrochemistry is also very useful. People would wonder why corrosion. So the simple answer is electroplating devices. And further moving on to my topic, I worked on zinc-bromine redox flow batteries. So what are zinc-bromine redox flow batteries? Zinc-bromine redox flow batteries are huge batteries that is used to store the renewable energy resources, which are intermittent in nature. And we have a catholyte and anolyte in place of a cathode and an anode, because here the charge is stored in form of electrolyte and not in a very solid state. So my focus is on the catholyte part, where there is a conversion of bromide to bromine during the charging process and the vice versa reaction during the discharge process. It involves a two-electron transfer, which suggests that the reaction in itself is complex. It is not a single electron transfer, which is very straightforward. So since we have a multiple electron transfer, the reaction kinetics of this reaction is really slow. So we have to use a tool to enhance the performance of this catalyte and this reaction in particular. Any reaction would have its own limitations, and this reaction is having its own limitation. So catalysts are used to improve the efficiency of this reaction. It acts as a support system to enhance the kinetic parameters. In my study, I have used carbon nanotubes as the electrocatalyst due to its advantages like electrical conductivity, mechanical strength, high surface activity, and wide operational potential window. Because this reaction operates at a really high potential, so we need some electrocatalyst that can actually not disintegrate with such high potentials. And the most important thing is the chemical inertness of the carbon nanotubes, because bromine, as we all know, is very corrosive. So we need an electrocatalyst that can withstand this corrosive nature of bromine as well. So hence, in my study, I have used carbon nanotubes as my electrocatalyst. Further, moving on to the experiments and result setup, we first conduct the glassy carbon electrode experiment, which is a substrate like a working electrode, where we study the bromide oxidation reaction in the sodium bromide solution, where bromide is sourced from, and we have a cyclic voltammogram showing how the oxidation occurs and how bromide is converted into bromine. Further, we also did a bromine reduction reaction, and here we sourced bromine molecules from bromine solution itself, and then we observe how the reductive peak would look like. And then we have the Tafel analysis plot given in the inset, and thus we calculate the transfer coefficient beta and alpha. So beta is 0.45, and the alpha, the transfer coefficient for a reduction reaction, is 0.33. So this value suggests that there is one single electron transferred at one particular time. And as I discussed earlier, bromine-bromide reaction have two electrons. So we have multiple electron transfers occurring in this reaction at the glassy carbon electrode. So now that we know how the reaction occurs at a bare electrode, we then move on to study the diffusion coefficient on the glassy carbon electrode using the Randall-Selchuk equation. It gives us the diffusion coefficient value for bromide and bromine of our experiment. And then we move on to study the carbon nanotubes, like how, now that we know how a carbon surface would respond to the reaction, we need to know how our electrocatalyst is performing for this particular reaction. That's where the traditional drop cast experiment comes into play. Here we have our carbon nanotubes dispersed in a solution, and then the dispersed solution is drop casted over the working electrode, that is the glassy carbon electrode. We dry the electrode, and then here I have taken optical microscopy images of two different concentrations of carbon nanotube drop casted on the glassy carbon electrode. One is 6 microgram, and it's only covering 20 to 30% of the glassy carbon surface, whereas the 30 microgram drop cast, of course, covers the whole of the glassy carbon electrode. And here is a SEM image of the drop casted carbon nanotubes, which has a huge lumps of agglomerations happening, and then there are voids and pockets on the surface. We will look onto it later why we need to look into the SEM image and why is agglomeration matters at all. So this is how a traditional drop cast experiment is done. And then we record the cyclic voltammogram for the drop casted electrode. We compare the drop casted electrode with the bare glassy carbon electrode, and of course we see a huge increase in the peak current, and the peak-to-peak separation also is decreased. So usually any electrochemists who work on energy sector and who work on electrocatalyst would define this as the electrocatalytic performance of the carbon nanotubes. So when they see that there is an increase in the current and there is also a decrease in the peak-to-peak separation, they suggest that, okay, now the reaction is more reversible, and thus the reaction rate is also improved. But is it the true thing that is happening with the carbon nanotubes is what we will look into further. To study, now that we know how a group, like an ensemble of carbon nanotubes would respond to the bromine-bromide reaction, we need to study how one carbon nanotube would react to that particular reaction. That is where the nano impact studies comes into play. So we have a connecting wire, and then we have our homemade carbon wire microelectrode of 7-micron dia. So here we have the carbon nanotubes dispersed in the bromine-bromide solution, and then by a Brownian motion, this carbon nanotube colloids stochastically with the carbon wire electrode, and thus we observe the current transient. So here you can see a very brief introduction about the carbon nanotube, how the impact experiment is observed. When there is no collision of any carbon nanotube with the electrode, the surface, like there is no current observed at all. Hence, we conclude that there is no bromine-bromide reaction happening on that particular surface. And when the very first introduction of the carbon nanotube to the microwire, there is a sudden increase in the current. And thus, as long as the carbon nanotube resides on the carbon wire electrode, there is a current observed. And once the carbon nanotube departs from the carbon microwire electrode, there is sudden step down of the current. This suggests that this particular current is contributed only by the carbon nanotube and not by the carbon wire electrode. Hence, so this is how we study the carbon nanotube impact experiment. So why do we actually need them? The answer is, as we have already seen the SEM image, we could see like huge agglomerations of carbon nanotubes tangled together, because though the diameter is in nanometers, their length is in few microns. So the possibility of these carbon nanotubes getting agglomerated on a carbon surface is huge. What happens when it gets agglomerated is that, as you can see here, the few pockets, the electrolyte gets trapped in those pockets of the carbon nanotube, and these act as a nano level or micro level thin layer cell instead of a catalyst. So there are two different types of diffusion that can possibly occur in such surface area. And to identify if there are like two different diffusions happening, which is thin layer diffusion and semi-infinite diffusion, we have a logarithmic plot of peak current versus scan rate, and the gradient value suggests if the diffusion is only semi-infinite or a mixed mass transport diffusion. So what happens is that if you get a gradient value of 0.5, then there is only semi-infinite diffusion that happens. And if the gradient value is 1, then it's purely thin layer diffusion. Any value between 0.5 to 1 suggests that there is a mixed mass transport happening. And here, as you can see, the broadcasted electrode shows almost 0.7 and 0.7 gradient, which suggests that there is a mixed mass transport happening. Whereas, to eliminate all these agglomeration effects of the carbon nanotube, we need to study the true reaction kinetics of one single carbon nanotube. And that's where the nano impact experiment helps, and it eliminates the agglomeration effects. So further moving on, we did nano impact experiment, and these nano impact experiments are done by chronoamperometric studies. We have where applied potential, the potential is applied for studying that particular reaction. For instance, the bromine oxidation reaction was studied in sodium bromide, and the applied potential was 1.3 volts. So here we can see that the oxidation impact is observed for the carbon nanotube, like a single carbon nanotube. And similarly, we also did the same study for the reduction reaction at applied potential of 0.2 volts. And we studied the reduction nano impact signals. So what we do is we do these experiments at different applied potentials over a range. And here you can see we clearly get a sigmoidal curve corresponding to the contribution of current by a single carbon nanotube. And we use the simulation method, the DigiSim simulation, involving inputting all the parameters that we have obtained for this experiment, and then we calculate the rate constant. So this rate constant is nothing but the kinetic parameter, like how fast the electron transfer is happening for that particular reaction is usually studied. So here, for the bare glassy carbon, we get the rate constant in terms of 10 power minus 5. Whereas for the nano impact experiment, where we get the rate constant for the contribution of one particular nanotube, we have, of course, improved performance, but it is not as huge as expected from the dropcast experiment. So that is why we need to look into a single nanoparticle. So now we conclude that nanotubes are not very, very good electrocatalysts. They do have a mild catalytic performance towards this bromine-bromide reaction, but not as expected from a traditional dropcast experiment. So to conclude, we have did bromine-bromide redox reaction study on both classic carbon electrodes and multi-wall carbon nanotubes dropcasted experiment. And then we employ nano-impact electrochemistry to study the contribution of single carbon nanotube. Simulations were done using the parameters obtained from both classic carbon electrode surface and the impact experiment to obtain the rate constant for this bromine-bromide redox reaction. And this overall study concludes that there is only mild catalytic activity that is contributed by the carbon nanotubes. I have to thank my professor, Dr. Richard Compton, and the Commonwealth Scholarships for giving me the fellowship, and the department, University of Oxford, MHRD India, and my group members, family, and friends. Thank you so much. I'm happy to have any questions, please.
Any queries?
Ma'am, can you detail about the chronoamperogram study? Can you explain?
Yeah, sure. So chronoamperogram study is done in a very similar 3-electrode system. And in that experiment, what we do is we disperse our nanoparticles of interest into the analyte solution. And then we apply a particular potential to study the impact experiment, that is like the current. So you apply a constant potential to the cell. And then we have the current response versus the time. So if you record the chronoamperogram for certain seconds or minutes at an applied potential, we get the current response contributed by the electrode. Here for nano impact experiments, the electrode is the carbon nanotubes, and the microwire electrode is used as a support system as a conductive material for the carbon nanotubes.
Okay, ma'am, thank you.
Okay.
Ma'am, any other electrocatalyst other than this carbon nanotubes?
So there are a wide range of electrocatalysts that we can study. For example, metal oxides and even carbon nanotubes and graphene oxides can be studied. Our group members have extensively worked on techniques like studying hydrogen evolution reaction and oxygen evolution reaction on graphene oxides, and then some metal oxide dopings have been done on carbon nanotubes itself, like palladium metal has been doped over the carbon nanotube, and then this has also been used. So there are a huge range of electrocatalysts. Any electrocatalyst that falls into the category of nanoparticles can be studied using this reaction if they are stable in the electrolyte.
Okay, ma'am, thank you.
Okay.
Ma'am, you have shown some experimental results. That is the graphical representation. Can you please say what is the software that you are used to get the output? That is the current versus time, etc.
This is a typical potential stat that we use, and if you for this particular, we use the software Nova 2.0 version, and we can use any potential stat which has an inbuilt software for running chronoamperograms. We use a different software for do the reaction rate studies. This simulation is a programming software, so we use a DigiSim software for calculating or obtaining the theoretical setup. So here the black line is a fitted one, which is a simulation result, and the red dots are the experimental ones.
Thank you.
Thank you.
Any more queries?
The zinc bromine redox flow battery. What about the ease of handling? Is it easy to handle that? That is, I know that bromine is highly reactive. What about the how to work on it? Is it easy to handle or easy to work on? When we see
So
about
usually, when they actually have a prototype earlier, now I work on the fundamentals of the reaction. Earlier, I was used to work on the prototype of the whole battery itself. So they have some certain complexes, coordination complexes that happen. So they add ammonium salts to the electrolyte. So this forms complexes with the free bromine. So there is no escape of bromine to the atmosphere, which makes the whole system more safe rather than there is like bromine evolution. So they also add some ammonium salts into the electrolyte to capture the bromine molecules. Yeah.
okay, ma'am. Thank you.
Okay.
Any more queries? Ma'am, can we recycle the battery which consists of nanoparticles?
So the electrocatalyst is usually coated over the electrode surface, and the electrocatalyst life cycle has not been studied, at least in my study, but reports have suggested that this can. Am I audible?
Yes, ma'am. Yes.
Yeah. As I was saying, the bromine bromide reaction, like the electrode is actually coated with the carbon nanotube or any catalyst for that matters. So what happens is that the carbon nanotubes or any carbon molecules are hugely stable, and they are quite inert to all these reactions. So they just act as a surface where the reaction is happening, and it's usually stays there for a really long time. So we don't have to actually, it doesn't corrode or it doesn't come off with the electrolyte. It stays on the electrode, just like your if you want to change it or recycle it, you just have to remove it and then recoat it with another layer of carbon nanotubes. So that's how it practically works in a really large scale of batteries.
Thank you, ma'am.
Thank you.
Any more queries? Thank you, ma'am. With deep
Thank
sense
you.
of appreciation, I thank the speakers, Ms. Ravalika Shaji and Archana, who spent their time by gracing the occasion. Today, we had the opportunity to hear your thoughts, and this is very useful for us. I thank you, ma'am. Then I thank Dr. Praveen Narayana Perumal, the speaker of yesterday. Thank you, sir. I thank all the speakers of the 2 days conference. Then I thank our coordinators, Dr. Sahai Ruben, Head Department of Civil, Dr. Radhika, Head Department of Chemistry. Then I thank the management of Rogini College of Engineering and Technology for giving the opportunity to conduct this international conference. I thank all. Then I thank all the participants for their interest towards this session. Thank you. Participants, you can fill the feedback form that's in the chat box and you can send it. Thank you, one and all. Thank you, ma'am.
Thank you. Bye.
Okay.
Bye,
Thank you so
thank
much.
you.
Thank you, sir. Thank you. Thank you.
Thank you.
Ma'am, the feedback link is not opening, responding. Hello, ma'am. Hello, ma'am.
Feedback. Wait a minute. Wait a minute. இப்போ ஓகேவா?
சார் ஓபன் ஆகுது. ரூபன் சார் ஓபன் ஆகுது.
So now the link is open. You can check.